Hello and welcome back to the video lecture series on statistics for machine learning, and we are going to do the inferential statistics and the concepts of sampling theory, right? Now, before we go to the analogy, I mean rather how machine learning leverages the concept of sampling theory, let's quickly cover a couple of other things. There are two laws basically which kind of govern that the samples can reflect the characteristics or rather of the population, or rather we can use the samples to kind of have a inference or infer about the characteristics of the population. So the first important law is the law of statistical regularity. What does it say? It says that a sample of reasonably large size, this is a very important point, a sample of reasonably large size when selected from a population, obviously in a random fashion, is almost certain to represent the population. Okay, the characteristics of the population. So there are two important terms here. One is reasonably large size, a sample of reasonably large size. That means the sample should have number of units which can be considered to be reasonably large. Okay, and what is that? We will come to another law for that. Okay, and when we have that, the measures being done on the sample, they almost certainly represent the characteristics of the population. So those measures drawn on the sample are almost certainly going to be close to that of the population. So that is the law of statistical regularity. That's one very important law. The other one is known as law of large inertia of large numbers. What does it say? The samples of large size again show a high degree of stability. Okay, so understand one thing. If I am trying to draw the sample from a particular population, more often than not, why I say more often than not, I'll come to that. But more often than not, since we are drawing random samples, we are definitely going to come up with a separate set of units as a part of the sample, right? So when we choose the units from the population and put it in the sample, almost all the time, we are going to end up with a different set of those units which become a part of the sample. But the law of inertia of large numbers says that the samples of large size show a high degree of stability. That is, the results obtained from the samples are expected to be close to the population and close to each other. So when we draw a sample 1 versus when I draw a sample 2 versus when I draw a sample 3 and make the measurements, say for example, a particular statistic, say for example, sample mean, more often than not, it will happen that they are going to be very close to each other and very close to the population. I mean, the measure for the population, right? So that's another very important thing. One term I would refer here, whenever I make the measurements for a particular sample, that is called statistic. And when I make the similar measurement for the population, that is known as parameter. Okay, this is something we need to know. We'll study more about it. Okay, now we come to where these concepts have been used in machine learning, right? We need to understand that. So say for example, I'm sure most of you know about machine learning to a large extent, and in machine learning we have an input data set, right? This is my input data set. And what do? I take a portion of that input data set and segregate that portion. I keep out this portion, or rather, I call it as hold out. I hold out this portion, okay, and the remaining larger portion I use for training my model, okay. So, say for example, typically a number like 70% is used for training the model, and a number like 30% is used to test the model, right? Now, here comes the role of sampling theory, right? I have to draw. So if I consider the whole set as my population. Now I draw a portion of this which I call my training data set, or rather my training data, right? And that's equivalent to my sample. Now here when I draw this training data, I need to be very sure that there is no major change in the characteristic of the population, that is the whole set of data, and this sample, that is the training data. I need to be very sure about that. How do I do that? I follow the practices of sampling theory. How? I draw the units for this sample or for this training data by doing a simple random sampling, SRS. Okay, I draw them with simple random sampling. How can I do that? So say for example there are multiple rows here, okay, and each of these rows I can give a serial number, say 1, then I give a 2, okay, I give a 2, I give a 3, so I give all the serial numbers here. Okay, now when I do say here, say for example 21, 26, like this. Okay, now when I draw and when I pick up this training data, I use the random number table again. Okay, and that random number table will pick up serial numbers in a very ad hoc or random fashion. So say for example first the number picked up is 52. Okay, so what I will do, I'll go to the row number 52 and mark that record as a training record. Okay, I mark this as a training record. Then say for example I have a 15. Okay, so what I will go, I'll go to the row number 15. Okay, and that row number 15 I mark it for the training record. Okay, and again I am drawing the training data. What happens is I can draw more such samples, multiple such samples. So this is sample 1, I can draw a sample 2, like this I can draw multiple samples. Where do I do that? When I do something for like a, I'm sure all of you have heard this, the concept of cross validation, right? The k-fold cross validation, right? So what is a cross validation? What does it do? Basically, it divides the whole portion of the input data into k folds or k groups, and which units belong to each of these k groups is completely random. It is done using the concept of sampling theory. And when I pick up a particular fold, basically I pick up one fold for test data and the remaining k minus 1 folds I use as a training data, right? So that process I keep on repeating for multiple times. How many times? K times. Each time I take one particular fold as a test data, remaining k minus 1 folds as a training data, and keep on repeating this process. So here we are using the concept of simple random sampling without replacement. Without replacement, I mark simply each of the folds are going to contain certain few units, and those units are completely randomly allocated to the folds. And each time I have one fold being marked as a test data and the remaining k minus 1 folds as a training data, right? This is how I do that k-fold cross validation, right? K-fold cross validation. Now this is a concept where I use the concept of SRS WOR, or without replacement. Now you may ask, where do I use the concept of SRS, or do I really use it, SRSWR with replacement? Yes, I do definitely do that. How? Say for example, when I am using the concept of say this thing, bootstrapping, right? So there I use the concept of simple random sampling. So in bootstrapping, what we can do is we can have one particular unit or one particular record being made a part of the sample multiple times, right? Or being a part of the training data multiple times. Why do we do that? Because, or rather, when do we do that? When we have a input data which have a smaller size. In that case, we have no other option for other than doing this. Now again, the concept of random number table, I mean, we definitely use that here, I mean, the same way as we have discussed. But one thing that I want to mention here is, so I know that, I mean, I've told that there are different, say, numbers being given as a part of the random number tables, and what we do is we can just start from an arbitrary place and we can just keep on picking up values from here, right? So what we can do is we can start from here and then pick up each of the two-digit numbers from here. Okay, but the thing is we can also start from here, and then in that case the numbers being picked up are going to be completely different, right? So that's how the training data can be different each time, right? When I do the random sampling, each time I pick up the training data using random sampling technique, it can give a completely different training data, and it can give the results also a little different. But here we can also use the concept of seeding, right? We use random seeds. What does it do? It basically points, makes sure that it points to the specific place in the random number table, so that if it always starts from there, the serial numbers which are going to be picked up are always going to be the same. So the training data will always have the same composition each time. And when I use the training data to make the specific experiments, our experiments are also going to have the same results, right? So this is where the concept of random seed. So if you look at a Python code or whichever language you work on, you will see the concept of random seed. When I do a train test split, right? There's a function in sklearn called train test split, right? When I use that function train test split, I have a the parameter called random seed, and I mention a specific value out there. Even when I use R, there is a parameter for seed. So what it does is basically it points to the same position of the random number table, so that the composition of the training data remains the same, because the same set of serial numbers are going to be picked up. So the same set of units are going to be picked up as a part of the training data, right? So this is a very important concept, and this is how sampling theory is being used. The concepts of sampling theory is being used in machine learning. I hope you understand this concept. Okay, so let's come back and talk about some more concepts in sampling theory. Stay tuned. Thank you very much.